Hey everyone, welcome into this lecture video on partial fraction decomposition. In this lecture I'd like to give kind of an outline of how to perform the partial fraction decomposition of a rational function, and then do just a couple of quick examples where maybe we'll see how it goes. So here's the setup. So let's suppose that we have a rational function r of x, and remember a rational function is a ratio of polynomials, so p of x over q of x. So here, p and q are polynomial functions. All right, then the partial fraction decomposition, there's a couple of rules that I'm going to write down, and you got to kind of go in order, but they're not necessarily, it's not necessarily a list of things that you should follow directly. I mean, it kind of is, but so here's the things to look for. Number one, if the degree of p, the degree is the highest power, right? The highest power on any exponent, the largest exponent on the polynomial. So if the degree of p is greater than or equal to the degree of q, then you need to perform long division. So perform the division. All right, and then what you'll do is once you do the division, you'll probably end up with a remainder. If not, then you're good to go, right? Then you just have a polynomial. But if you end up with a remainder, then you'll perform the following steps. Whatever comes after this step one, you'll perform those steps on the remainder term, okay? So step two is to now, once you, at this point, I'll put this in between here, right? So once we've done this, now we can assume that the degree of p is less than the degree of q. So the largest exponent on the numerator is smaller than the largest exponent in the denominator. So at this point, step two is it's step one of the process. So you have to, number one, make sure you're in the right realm, right? And then at this point, you need to factor q completely. And there are a whole bunch of, frequently when I go through this lecture in an in-person class, I'll remind everybody about all the different theorems that lead up to the fundamental theorem of algebra, but you guys can review that. So let's review, I'm going to write this here. So review the fundamental theorem of algebra and all of its friends. So there's a factor theorem, there's a rational root, there's all kinds of different theorems that go together with the fundamental theorem of algebra. But basically what we find out then is that we can factor our function q of x always into a product of linear and quadratic polynomials. So I'm going to write it like this. It's going to become a factor of q1 of x to the power r1, so that's the multiplicity, times q2 of x to the power r2, etc., all the way up to this qn of x to the power rn. And by the way, the degree of this polynomial times the multiplicity added up, that has to equal the degree of q. All right? So in other words, recall, this is part of the fundamental theorem of algebra, so I said I wasn't going to go too deep into it, but at this point, the degree of q, so in other words, this can't go on forever, right? This factoring can't go on forever. There's an end to it. So the degree of q is equal to the sum, I goes from 1 to n, of ri times the degree of qi. Okay? So that's got to be equal to the degree of q. All right, so again, take some time, pause this video, go review the fundamental theorem of algebra and all the other theorems that are surrounding it. But the point here is that we can factor this polynomial q, and then step 3 at this point, I guess it is to break down our initial fraction, our rational function, into partial fractions, okay? So we now need to break down this fraction, p of x over q of x, into partial fractions. These are like, I mean, I was going to say they're like factors. They're not really, but they correspond to the factors of q, okay? So I'm going to write this as according to the following rules. All right, and so the rules I'm going to break down into a table. So this is the factor of q that we're looking at. For each factor of q, we're going to get partial fractions, all right? And then over here, I'll write down, here's the partial fractions that we'll get. All right, and so here are the different cases. Let's suppose, so I'll call this A, 3a's. Let's suppose the degree of q sub I is equal to 1. So q sub I is any factor, one of the factors. It's the q term. It's not the multiplicity, right? But let's also suppose that the multiplicity, r sub I, is equal to 1. So we have a linear factor that only occurs once as a factor. All right, in this case, our partial fraction is going to be some unknown constant, I'll call it a sub I, over q sub I of x, right? So this is a constant over the linear term. So over here, in this part of the table, all the a sub I might end up with b sub i's. These are real number constants, okay? By the way, that's an unknown constant. Part of this process is going to be that we have to figure out what these constants are. All right, but there's an unknown constant. So what about if the degree is 1? So we have linear factor. So degree of q sub I is 1. But the multiplicity is greater than 1. Well, now we need one of these for each power, actually. Okay, we need one of these for each power, each multiplicity, for each multiplicity. And so now what we end up with is our partial fraction is ai1 over q sub I plus ai2, so a different constant, ai2 is a different constant, over q sub I of x squared, plus, and then you have all these terms all the way up to ai, whatever the multiplicity is. So if it's 5, we now have 5 terms, and this is then qix to the 5th power. I said 5, I made up a number, but really, whatever it is, it's got to be the multiplicity, right? So the r sub I power. And this is a sum now, and we want to leave it as a sum because it's broken up into a sum of constant term over linear term, constant term over linear term squared, all the way up to constant term over linear term to the whatever r'th power, so the multiplicity's power. All right, and so there we go. Next possibility, what if we have the degree of our factor is equal to 2? So when you go back and you do review the fundamental theorem of algebra, you can always break down your denominator, your polynomial. You can always factor it into linear and quadratic terms, okay? So in this case, let's say, all right, well, what if this is multiplicity 1? Well, in this case, because this is a quadratic denominator now, we actually need a linear, the possibility at least, of a linear numerator. So in this case, what we do is we set our partial fraction equal to a sub I times x plus b sub I. So that's a linear term because this x is a variable. A sub I, b sub I, those are constants. X is a variable. And then this is just divided by the quadratic q sub I. All right, so that's when the denominator, so the factor, is quadratic. Irreducible, by the way. So irreducible quadratic. You cannot factor it using real numbers, real number coefficients. All right, and at this point, you can probably guess what's going to happen when there's multiplicity. Well, you just have to repeat this, right? You have to repeat this linear over quadratic term for each multiplicity. So if our degree of q sub I is 2 and the multiplicity is greater than 1, then what do we end up with? Well, we have our a sub I 1 times x plus b sub I 1 over q sub I of x, plus the next term is going to be a sub I 2 times x plus b sub I 2. That's over the squared term squared. And then this will continue just like with the linear ones. It'll continue all the way out to a sub I r I x plus, I'm running out of space here, that's b sub I r I, and then this will be the total multiplicity here. So the idea is that you need one term for each multiplicity. If your denominator is linear, you just get a number on top. If your denominator is quadratic, you get linear on top, and then the you need one fraction for each multiplicity. All right, so this is and then by the way, what do? Well, then at this point, your p of x over q of x is equal to, what do? You write down, you take all these partial fractions that you've added up, and you rewrite your fraction here has to be equal to the sum of all of the partial fractions that you've just determined. Okay, sum of all the partial fractions. So by the way, to get all these terms, so to get terms that look like all of these at the same time, the degree of your polynomial in the denominator would have to be pretty large. And for most of what we do in this class, the denominator will not be so large. So this is like intimidating to even think about, but let's do a couple examples to see how it's going to work functionally. So let's say we have this fraction, 1 over x squared plus 6x plus 8. All right, we want to find the partial fraction decomposition of this. Well, first of all, the degree of the numerator is just 0, right? It's just a constant, so it's 0. And so it's good, right? So it meets the criteria number 1. Number 2, we have to ask, can we factor this denominator, right? So this is our q of x in terms of my table. So q of x is x squared plus 6x plus 8. Does it factor? Oh yeah, it factors, right? It factors to be x plus 2 times x plus 4. So these are both linear factors, and their multiplicities are 1. If there's no exponent written, then the exponent is 1, right? And so what does that tell us? Well, it tells us that we should have one unknown term for this one and one for this one, right? So in other words, we're in case 3a for both of these, right? In this case, I'm not going to write a sub 1 and a sub 2 because the order doesn't matter and it's going to get a little weird. So I'm going to just write this as follows now. A over x plus 2, unknown constant over the first factor, plus unknown constant over the second factor. It's got to be a different unknown constant, so I'll call it b. All right? And so the partial fraction decomposition says that we can find a and b for which this sum of fractions on the right is equal to this fraction on the left. How are we going to find a and b? Well, add these back up, right? So the idea is that we should be able to add these up and get this back. So how do you add fractions? You find a common denominator. This is pretty straightforward because there's only two fractions, so you have to cross multiply here. You end up with a times x plus 4 plus b times x plus 2 all over x squared. It multiplies out to be the same thing, right? Because that's where these factors came from. And so now when you look at this, you say, okay, I want these two fractions to be equal to each other. Their denominators are already equal. So for the fractions to be equal, what's got to be true? Their numerators have to be equal, right? And their numerators have to be equal for all values of x, right? These have to be equal to each other for all values of x. When I say all values of x, I mean even the ones that might make the bottom bad, right? So what we get, though, is this equation. So we get this equation to solve for the unknowns. This is 1 equals a times x plus 4 plus b times x plus 2, again, for all x, right? So one method for solving for these a and b is to make what we call convenient values, convenient choices of x. So if we're going to make convenient choices of x, we want to choose a value of x that makes one of these go away. So let's start with this one. We want to get rid of this term. So let's choose x equal to -2. And then we'll plug in -2 everywhere in this equation. On the left, there's no x, right? So it's just 1. On the right, we get a times -2 plus 4 plus b times -2 plus 2. Well, the whole idea is that this one's no longer contributing, right? That's gone. And then this one, our equation now says that 1 is equal to 2a. And so this says that a is equal to 1/2, right? So now we've got a. We can do the same thing by isolating b, right? By choosing x equal to -4. So if x is equal to -4, then this equation says that 1 is equal to a times -4 plus 4. We know what a is, but it doesn't matter because that's going to be 0, right? Plus b times -4 plus 2. Again, that term's gone. This one is going to be -2b, right? So in this case, we get 1 equals -2b. and that tells us that b is equal to -1/2. All right, so what did we learn? Well, we got to now go back up. Our goal was to get this decomposition, right? So here's what we've learned. We have our a, we have our b. We know where they go, right? What we've learned then is that 1 over x squared plus 6x plus 8 is equal to 1/2 over x plus 2 plus -1/2 over x plus 4. Or another way to write this, if you're thinking of, we're going to want to integrate these probably. I mean, that's what section of the... This is not really related to integrals at all right now. This is just algebra. But our goal is going to be to use these to integrate, right? So we get 1/2 times 1 over x plus 2 minus 1/2 times 1 over x plus 4. And this is what I would say is a nice form of the partial fraction decomposition of this rational function. All right, let's do a couple more quick examples here to see how some of the other rules work. For those ones, I'm not going to solve for the coefficients, maybe. I'll do one more where I solve for the coefficients. But this next one, I'm not going to solve for the coefficients, so I don't want this video to get too long. It's already too long. But x cubed plus x squared minus x minus 1, it's x over all that. So again, degree of the top is less than the degree of the bottom. So our job now is to factor the bottom. And we can see just by plugging in that 1 is a root, right? So if you plug in 1 for x, you get 1 plus 1 minus 1 minus 1, 0, right? And again, when you go back and you review, it's very important here. This is very important that you really do this, okay? When you go back and you review this, there is a theorem that says that if x is a root of the polynomial, then x minus 1 is a factor, or x minus the root is the factor. Okay, so in other words, since 1 is a root, then -1 is a factor. X minus 1 is a factor. 1 is a root. So what does this mean? Well, 1 cubed plus 1 squared minus 1 equals 0. So this tells us then that x minus 1 is a factor. And so then we can divide through and see what's left, right? Well, if we're dividing by -1, we can use synthetic division. And so in this case, we just set this up, our little synthetic division house, and we synthesize. And this is going to be 2, so that's 1, 1, 0. That's what we expected, right? We got 0. And so this tells us then what? This synthetic division here, that x cubed plus x squared minus x minus 1 is equal to x minus 1, that's what we divided by, times what? This is going to give us x squared plus 2x plus 1, but this term is a perfect square. So this term we notice is x plus 1 quantity squared. All right? And so that's this then, right, becomes our denominator. And now we want to apply our rules to write the partial fraction decomposition of this, at least with the unknowns, right? So we have two first degree factors. This one has a multiplicity of 2, though. So we know what to do with the first one, because that's exactly the same as what we did up above, right? So we get a over x minus 1, plus with this one that has a multiplicity 2, we have to go back up. When the multiplicity is 2, we need one term for each. That's what the rule says, right? One term for each of the multiplicities. So this then becomes b over x plus 1 to the first power plus c over x plus 1 squared. And so there's the partial fraction decomposition. There's still some work to do to find a, b, and c, but this is the general form. So this is the general form of the partial fraction decomposition. So by the way, recommended exercise. This is an implicit exercise. Anytime I don't do something, it's for you to do, right? So solve for a, b, and c. You'll notice that there's only 2 convenient values, but there's 3 unknowns. So you can find 2 of them by the convenient value method that we chose up here, or that we used up here. And then for the third one, you'll have to choose some other number, any other number. But once you know 2 of them, you choose any other number, and you'll be able to find the third one. So please do that. Now here's my last example for this video, and this one is x squared minus 1 over x squared plus this denominator is already factored for us. All right, and it's factored into quadratic times linear. This quadratic term is irreducible. You cannot factor this with using real numbers, right? So cannot be factored using real numbers. The degree of the bottom, by the way, is 2 plus 1. It's 3, right? The degree of the top is 2. So this is good to go. We just need to write out the partial fraction decomposition. Again, we know what to do with the linear term, so let's start with that. So this is a over x plus 2, plus, then we need to deal with this term, right? So the quadratic term, if we go back up to our table, quadratic term fits in, and with multiplicity 1, fits in item C here. We need a linear term of unknowns on top. So it's going to be bx plus c with the letters, if I'm just using, chronological alphabet letters here, all over x squared plus x plus 1. And now for this one, I would like to solve for the coefficients, because this one, the convenient values, they're not so convenient anymore. Yeah, so let's see how this works. At this point, we need to add these up, right? That was our rule. So we need to cross multiply. And again, there's only 2 fractions, right? So if there's more than 2 fractions, you have to be a little more careful about how you work this out. And as you go along, you'll find tricks to it. I'm going to let you discover those on your own, because I want to make sure you're thinking the right way. But just to add up these 2 fractions, we get this. And by the way, the denominator is exactly what we wanted. So again, those are the same. Ignore them, right? And so our equation now says we have to set the numerators equal, right? So x squared plus 1 has to be equal to this right here, this entire sum, product, whatever it is. So a times x squared plus x plus 1 plus bx plus c times x plus 2. And then we need to multiply this all out. So we have x squared minus 1 on the left-hand side. I'm going to just multiply everything out, and then we'll regroup. So ax squared plus ax plus a plus bx squared plus, what is this going to be? Well, I'll just write it out. So this is going to be 2bx plus cx plus 2c. All right, and now let's group this by powers of x. All right, so I'm going to make a little table here. The x squared terms, on the left we have how many? So these equations have to be equal, right, for all values of x. That means the powers of x have to have the same coefficients. So on this side we have 1x squared. On this side we have a plus b. A plus b. All right, what about the x terms? Well, there's none on this side. There's no x, right? So there's 0 here. On the right-hand side we have a plus 2b plus c. Right? Ax plus b, 2bx plus cx. And then what about the constant terms? Well, on the left-hand side we have -1. And on the right-hand side we have a plus 2c, right? So a plus 2c. All right, and now we have a system of 3 equations and 3 unknowns. The 3 unknowns are a, b, and c, right? The 3 equations now are just equations with numbers, and we need to solve this somehow. So there's a couple ways to do it. One way is to solve each of these for, say, b and c, and then plug those into this one to find a, and then go back to the other ones, right? So for example, this you could write as b equals 1 minus a, and this one you would write, what, 2c is equal to -1 minus a, which means that c is equal to -1/2 minus 1/2 a. And then each of those go into this one, right? So here we have 0 equals a plus 2 times 1 minus a minus, so plus c, right? So -1/2 minus 1/2 a. And let's see how this all works out. Here we have 0. We have a, I'll group these together this way, a minus 2a minus 1/2 a plus 2 minus 1/2. All right, just grouping these together. So here, what do we have? We have, this is -5/2 a plus 2/2, so -3/2 a, and this is going to be plus 3/2, right? And so what's a got to be? Just by looking at this, a has to be 1, right? And so a is 1. If a is 1, this tells us that b is equal to 0. And if a is 1, this tells us that c is equal to -1, right? Just by knowing a, we can find the rest of these. And so once we've got those, then we can just plug back in up here. So now we know that x squared minus 1 over our denominator, x squared plus x plus 1 times x plus 2. This is going to be equal to 1 over x plus 2 plus, so minus 1 over x squared plus x plus 1. All right, and there's the partial fraction decomposition of this rational function.